everyone. My name is Symeon Christodoulou. I'm a professor at the University of Cyprus. Apologies if the presentation is not directly linked to the AR/VR session. It was scheduled for another session and we had to reschedule. It's primarily on digital twins and infrastructure management, okay? So I will try to make it as interesting as possible. All right, so the title is Roadway Pavement and Drivers Ride Quality Assessment using smartphones or smartphone-like sensors and participatory vibration sensing. The work is funded by the European Space Program Agency through a generous grant, and also by the government of Thailand, where the pilot case is about. Okay. So the scope of the work is to develop low-cost technologies for the assessment of roadway pavements, to test these technologies in real case pilot studies, and to provide a low-cost yet accurate method of assessing pavements that leads to a low-cost pavement management system and an optimization of operations and maintenance for the cities, municipalities, Ministry of Transport, okay? So the idea is to, instead of using specialized vehicles to assess roadway pavements, to use smartphones or probe vehicles, participatory sensing in the sense that drivers or cars drive and collect data continuously, and to use this data to map the condition of the roadways in a system that can help you manage the roadways better, okay, and cheaper. Okay, from past works, we primarily have three ways of assessing pavements. One of them is based on vibrations, vibration sensing. The other one, it has to do with vision-based methods, cameras and videos, okay? And then the last one is laser point technologies. All of them, each one of them has some advantages and disadvantages. Some of them relate to the accuracy, some of them relate to the cost, some of them relate to the speed of collection, the data collection, et cetera, okay? But if you can collectively use the methods and pick the advantages of each one of them and combine them into a single unified integrated method, hopefully that would be a better approach. And this is basically what we're trying to do. We're trying to merge these three technologies into a single robust integrated platform system that can give us better and easier and cheaper assessment, okay? Three key findings of past pilot studies relate to the way the roughness, the pavement roughness is assessed and the inaccuracies in it, how you detect distress in the pavements, and by distress I mean anomalies like potholes. Okay, some of the methods, for instance, the vibration methods are good in detecting potholes and speed bumps. Some of them, like the vision-based, are good in detecting cracks, okay, but it's more difficult to use. Some of them, like the LiDAR, can measure also depth of the distress, but even that is not easy because if you're traveling at a speed, the LiDAR cannot quickly adjust to the data collection, okay? So we're trying to do this, to combine the three methods by also using crowdsourcing, meaning that we have a lot of data collectors, okay, either vehicles or people collecting the information and providing this information to a unified system. With regard to the vibration method that I'm going to talk about, we are using a smartphone-like sensor technology, and we're using a smartphone and the vibration of a smartphone that is on a car to relate the movement of the smartphone to the distresses on the pavement, okay? So we're looking at roll, pitch, and yaw, the vibrations, the rotations of the smartphone or the sensor, and we have a process, okay, that allows us to go from points, the vibration of the smartphone, to streets, to directions of the street, and also to the area, the municipality. So we start from points and we go all the way to the area, okay, to assess metrics that relate to the pavement. On the way, we use a lot of machine vision and machine learning techniques, artificial intelligence techniques. We use aggregation, clustering, classification techniques to go from points to roads, okay? And at the end of the day, we feed all the information to this pavement management system that allows us to prioritize the work. Work meaning which roads to fix, which roads to maintain, etc. Okay. The output is what you see here. On the left, you see points as they are collected from a smartphone. The points are colored based on the classification of the roll and pitch rotations. Those data points are aggregated and then clustered and elevated to the street level. Okay, so now you have, from points you go to streets, the different colors indicate the condition of the pavement. Okay. The more runs you make, the closer you get to the reality, in the sense that if you have multiple drivers, okay, at the end of the day you normalize the behavior of the car, and you assess, you reach a conclusion that combines the knowledge provided to you by all these different drivers. Okay. We ran this technology in Thailand about 2 months ago. We ran about 13 different runs, okay, in a period of 2-3 days. These are the distances. We covered about 73 kilometers of roadway. That took us about a couple of hours. It's not a big, you traverse the network in regular car speed, 50-60 kilometers per hour. So you get a lot of data, hundreds of thousands of data points. You classify them, we classify them in 5 scales, 1 being bad condition, 5 being, reverse. Class 1 means good, class 5 means bad, and you have some intermediate classes. We go from that point classes to the classification and grouping of roads. We evaluated primary, residential, secondary roads. We classified several segments. And at the end of the day, we evaluated the accuracy of the method with known metrics that the municipality had. It's not an IRI metric because they just got a specialized vehicle to do IRI testing. But we hope to be able, at the end of the day, to go from these classifications to a more internationally recognized classification based on the IRI. Okay. A couple of findings. The vibration-based method that we use gives you good enough results. It may not be accurate, but it's good enough, and it could be the basis for this pavement management system. To increase the accuracy, you can combine cameras. You can use the camera of the smartphone if you can avoid the GDPR issues. Otherwise, you can put a camera at the back of the car, a GoPro camera, because you need the fast shutter speed. You can have a GoPro camera at the back of the car and collect videos as well. That allows you to to map also the anomalies in the pavement, not just the condition, not just the movement of the car, but also the specific anomalies, the potholes, for instance. Okay, so we are now switching from GPS to EGNSS, which is the topic of this project actually. The EGNS provide even more accuracy to the level of centimeters. Okay, we're looking at normalizing, stratifying data, crowdsourced data, to avoid biases from the drivers or the cars. We are combining, further to vibration and video, we're now combining low-cost LiDARs, okay? And all this, as I said, in a combined integrated platform that allows us to go from the sensing to a number of sensors in between, okay? Databases, maps, and then at the end of the day, the pavement management system. The sensors we're using, okay, this section, are all low-cost sensors, okay? We are now aiming for a 1,000 euro cost per device, and for a more advanced system that includes the LiDAR to about 5,000 euro per device. That compares to the 500,000 euro per specialized roadway assessment van. Okay. All right. So, and the end users of this will be bus operators and the municipalities, primarily, and the Ministry of Transport. Okay. The project, as I said, is funded by the European Space Program Agency. It's called pavements. And these are the first deliverables of this project. The sensors, as you see, they're about this big, a box of this size for the sensors. Now we're expanding them with some additional sensors and some onboard graphics, machine vision processing unit that processes on the car all the the pavement anomalies. You go from the sensors to the GIS platform that shows the roll, pitch, and yaw metrics, videos of the anomalies, a map showing the condition assessment. Then you have a Python-driven machine vision, machine learning platform that analyzes clusters, aggregates data. And then to the right, you see an augmented reality application that allows citizens to collect data, not just drivers, and look at the data, the anomalies as they were detected by the machine vision and the vibration sensing technologies in an environment that is an augmented reality environment. Okay. And at the end of the day, all this information is linked to a smart city platform that shows municipalities where the anomalies are, the pavement anomalies are. So now you have an integrated system where people, drivers, municipalities, bus operators, and citizens can see all this information in a unified manner. And that concludes my presentation. I tried to be as short, as quick as possible. Thank you very much.